Here I'll be discussing about the system design of URL shortener like TinyURL or Bitly. So first I'll talk about the functional and non-functional requirement. Then we'll discuss about entities or APIs required. Then we'll have a high-level design, and lastly we'll deep dive into multiple sections. First, I'll be discussing the functional and non-functional requirements. So the first requirement we have is creating unique short URL for a long URL. So while creating the short URL, client can pass custom alias for the URL. So if some custom alias is passed, so that will be used as a short URL. Otherwise, the server will create one unique short URL. Optionally, client can also pass one expedition time. The next requirement is client can fetch or redirect long URL for a short URL. So usually, like for any URL shortener scenario, if we click on the short URL, we are redirected to the long URL. So that is the next requirement. One out of scope requirements I have written here. If I have time, I will cover that. That is the link analytics. It's basically if we want to keep track of the number of clicks per link, that we can do. Next, we'll be discussing the non-functional requirements. That's basically the qualities or the behaviors of this system. First, we need to think about the cap theorem, whether the system should be highly available or highly consistent. So consider if I am creating one short URL, do I need to access it immediately? Or if I can wait for a few seconds or more than that till the short URL is available for everyone. I think eventual consistency is fine here for this system. So we'll mainly consider on high availability. High availability means like the system will be available to create the short URL, system will be available to redirect the short URL. Next is latency. So for URL creation, short URL creation, the latency can be as low as possible. That will be determined by our design. We'll discuss that. But we need low latency for redirects, very low latency for redirects. So, and the redirect should be real time. Like let's assume it is around 200 milliseconds, 200 to 300 milliseconds, which is considered real time. Next, we'll consider the scale of the system. We'll do the scale related computations little later in the system, in the discussion, but consider the numbers here. We are having 100 million daily active users, but not everyone will create the short URL, right? So we're assuming roughly 100 million short URL creations for this discussion, and 10 billion redirects daily. Usually the redirects will be more than the short URL creation. So we are assuming around 10 billion redirects daily. Next, we'll discuss about the entities and the API. So we are having only three entities here: the user who is creating the short URL, the long URL, and the short URL. These three entities we have for our system. Next, we'll discuss about the APIs. So APIs are almost always related to these functional requirements. For all the functional requirements, usually we'll have one API. So the first API we need for creating short URL, and the second one is for redirect. So first one, for creation of short URL, we are using a REST post API. And this is /URLs. And what will be the payload? We need the long URL. For that, we want to create the short URL. Optionally, customers can pass one alias. That's why I have written it with question mark. Then also optionally, customer can pass one expedition time. That's also I have written with a question mark. Now next we have the redirect. For redirect, we need one REST GET API, and this is basically we are accessing the short URL itself, right? So the path will be, this is the short URL itself, and it will redirect to the long URL. Now there are two types of redirects possible. One is 301 redirect and another one is 302 redirect. Now 301 redirect is permanent redirect. Permanent as in if the browser will store the result, so next time when we'll hit the same short URL, it will not again hit the server. 302 redirect is temporary redirect. It's the temporary, so next time when we will access the short URL, it will again hit the server. So both are fine, but we can have a discussion with our customer, with our interviewer, which is perfect for this discussion. Now one thing to mention here is we are not adding the user details in the payload because that's not good for security reasons, because if we add the user details in the payload, then anyone can pretend to be someone else, right? So for that reason, user details are added using some authentication token like JWT token in the request header. Now next I'll have the high level architecture for this design. So I'm currently having one primary service that will handle both the work like URL creation and the redirection. So these two operations clients can have. So clients basically will be using one browser. So this service will take care of the URL creation and then storing it in one database. What will be the data model? It will be like we'll have short URL, long URL, expiration time, the creation time, the created by, right? And what will be the primary key? That will be the short URL, because we are accessing, the client will be accessing based on the short URL. And also we need to keep track of the user details, like user will have some ID, email or other stuffs that will also keep track of. I have not written completely, which is not very useful here. Also for ease of access, we can use one cache, right? So when users will use this redirect call to redirect to the long URL, we can easily fetch it from our cache. In cache, we can store it in key value pair. So key will be the short URL and value will be the long URL. So this cache will be a LRU cache. List recently used items will be evicted, and this cache, if the item is not present, if the short URL is not present in this cache, we can fetch it from this database. So this is the high level architecture. Next I will discuss about the scale. So we have already discussed that there are 100 million daily active users, and we are assuming 100 million daily URL creations are happening. So for a year, there will be 100 million into 365, and for 10 years, if you consider, there will be this much in multiplied by 10. Like this is 365 billion URLs will be creating. 365 billion unique URLs will be creating. Next, I'll calculate the TPS and QPS. TPS is the transactions per second and QPS is the query per second. So 100 million daily URL creations are happening. That means if we are assume there are 10 power 5 seconds per day. Usually it is 86400 seconds per day, but for ease of computations we are considering 10 power 5. So then per second we are having 100 million divided by 10 power 5 creation. 100 million is 10 power 8 divided by 10 power 5. So 1000 is the TPS. If we are having 10 billion redirects per day, that means 10 billion divided by 10 power 5. So 10 billion is 10 power 10 divided by 10 power 4, that is 10 power 5. So 100,000 is the QPS. Next we have next consider the data storage, the storage requirements. So this URL table, if we consider, uses the main table we have. So roughly, let's say 500 bytes per row. I'm assuming this is the like overestimation, but assume 500 bytes per row we are having. So 500 bytes, and we have 365 billion unique URLs for 10 years. So if 500 bytes into 365 billion, that is 500 into 400. I'm approximating this to 400 billion bytes, which comes around 200 terabytes. Now, based on this scale calculation, I will come up with few uh, decisions. First of all, you see this the QPS and TPS, they are very high, right? So and also this QPS is higher than TPS, right? So it's much higher than TPS. So we need to have a microservice based architecture so that we can scale the read and write part separately. Next, one thing is the storage database requirement. So what type of database do you think we need? So the storage requirement is 200 terabyte, which is not that big. Like, we don't have any complex schema relations, and also we don't need any complex joins for the read operations. And so we have decided that eventual consistency is fine. So if we use a NoSQL database, we are okay with it. But if we want to use a SQL DB, that will also work fine for our this scale 200 TB storage, and this 1000 TPS also is fine. This QPS and TPS also this SQL DB can handle. But we'll prefer a NoSQL DB like DynamoDB for this operation. Now next, I have redrawn the high level architecture. So here we have two services instead of one primary service. One is for URL creation and one is for redirect. And just because we have the scale is high, so we are having multiple instances of this service. Now, to handle this microservice architecture, we need one API gateway that will do few other things as well. First of all, it will do the API routing. The read request will go to this services and write request will go to that services. And also API gateway handles the authorization, authentication, rate limiting, load balancing, and few other things. Now here the database discussions we already had, and this is the rest of the things are same here. Next, we have to discuss the short URL size. So when we did our scale calculations, we saw that we need 365 billion unique URLs, short URLs, right? If we want to support the URL, if we are storing the URLs for 10 years maximum. So we have to generate our short URL in such a way so that we can create that many unique URLs. Consider if we are having base 10 URL. So base 10 URL is basically also consider that we are having 7 character short URL. That means we have 7 slots here. So in each of these slots, we have to have some characters to create the short URL. So if you are having base 10 URL, so that means for each of these slots, we can have any character from 0 to 9, right? So how many unique short URLs we can have? 10 power 7. That is very less than 365 billion. Next, if we consider base 62 short URL, that is, we'll consider these characters 0 to 9, A to Z, that is capital A to Z, and small a to Z. So then this 26 plus 26 plus 10, 62 characters we have. So for each of the slots, we have 62 possibilities. So for 6, if we are considering 7 character short URL, then we'll have 62 power 7, which is, if I'm not wrong, 3.52 trillion. This many short URLs we can generate. Isn't it too big? Like, we just needed 365 billion unique short URLs. Let's see if we have just 6 character short URL. So that will be 62 power 6 unique short URLs. So that is the close to 56 billion short URL, which is very less than 365 billion. So we definitely need at least 7 character short URL. Next, how we will create the short URL? So as we are having base 62 short URL, one thing we can do is randomly we can generate the short URL. Like, that is, like, for each of these slots, randomly choose between any of these characters, right? That is one way. Random 7 character base 62 key. Now, our next option is, we have the long URLs. We can hash the long URL, right, or use the part of this hash, and we can base 62 encode that part. What is the pros and cons of this first two techniques? Both are first scalable, reliable, right, but simple also, but there will be collisions. The first one, if you see, we are randomly generating the key. So of course there are chances of collisions. Second one, if you see, we are hashing the long URL, but there are chances the URL, we are taking the part of that hash or part of that URL, right? So that there also two URLs can be similar in the prefix part. So there are chances of collisions. Also, in some scenarios, this hash also can be similar. So in both of these two cases, we have chances of collisions. What are the other ways to avoid the collisions? That is using a counter, so that the counter values increment or always increment, right? So there are no chances of collisions. And the increment value, let's say starting from 1, 2, 3, 4, and each of these values will do base 62 encode these values. That will be our short URL. Now, what's the pros and cons for this counter-based approach? So, first of all, we are not having collisions because the counter values are always increasing. That's the main part. But the problem here is, consider this high-level design here. And where we'll place our counter in this case? So, will it be in the instance level, service instance level, or somewhere else? If we are having the counters for each service instance, so if we are having multiple instances of the service, then still there are chances of collisions, because both, let's say we are having two services, both can generate the same counter value, and then there will be collisions. So we need a centralized counter, right? So all the services will fetch the next counter value from this centralized distributed counter. So what should be this counter? Should it be a separate service or some other database, or what we should have? So just for the counter, let's not have a service. We can have one database. We'll see what kind of database we need for the counter. So what type of database for the counter? First option is SQLDB. SQLDB has the option of auto increment or sequence, right? If we can have one auto increment or sequence values, that will work as our counter. This is safe, simple, and very easy to set up. And SQLDB anyway by default supports the ACID properties, so there is strong consistency available for SQLDB. The problem here is it's harder to scale, right? So if you want to scale it, so SQLDB will be a bottleneck there. And there are write contentions, because the write operations here we are having this write TPS is very high. So write contention is also a problem for SQL DB. Consider NoSQL DB, Cassandra or DynamoDB. They don't usually have inbuilt increment operations, but we can set up it. But this is very little bit complex to set up. We need some custom logic for this increment operations, and this is eventually consistent. NoSQL DB is not highly consistent, so we cannot use NoSQL DB for that. Next option is Redis. Redis has a INCR increment operation for a key. So this is Redis is in memory and it's blazing fast. So we can use Redis for our operation, and Redis is basically single threaded, and this operations is increment operation is atomic. Also, Redis can be sharded for scalability. So we feel Redis is the best choice here. So we can have Redis as a counter. So we can use the same for this cache and this counter. We can have a single Redis for this, but I'm just drawing it separately for our understanding. So all this URL creation service will be accessing this Redis counter to increment the value. Now this is our final design till now. We'll just go through the functional and non-functional requirements once again to see if we have missed anything, or if we have to improve our design little bit. So functional requirements, we have already satisfied this too. Non-functional requirements, we have eventual consistency and high availability, low latency and scale. Let's see what all we have satisfied till now. So first is eventual consistency and high availability. So if we are having a database that is NoSQL, so it anyway supports eventual consistency and high availability. If we are using a SQL database, that is strongly consistent, but for high availability we need database replica. So we can have a replica for the database, and we need to take snapshot from the primary database periodically. Next, the services. We are using microservice based architecture. So we are having separate service for URL creation and redirection. We are scaling that separately. We are having this API gateway that will have the load balancer, and separately for each of this service also we can use some extra load balancer so that loads are properly balanced, properly distributed between the service instances, and so that the services are not bottleneck, because if one service goes down, the request will be redirected to other services. Next, this caches, are they single point of failure? So consider this redirect requests. If it goes to cache, one thing is the entry is not present in the cache, then it can be the cache can be down. In both of the cases, the service can directly fetch the data from database. It will take a little bit more time, of course, but the system is still available. What happens if the counter goes down? The Redis goes down, which is the counter, Redis counter. So in that case, that is a single point of failure, because we will not be able to create or serve the request for URL creation. So first thing what we can do is we can set the Redis counter in high availability mode. That's the first thing we can do. What next thing we can do? We can pre-assign the counter values to this service instances. Like, let's say I have divided the counter values in lakhs, maybe 0 to 1 lakh, 1 lakh to 2 lakh, 2 lakh to 3 lakh, and so on. And if we are having, let's say, 3 servers at present, it will be assigned like that. 0 to 1 lakh will go to first server, 1 lakh to 2 lakh will go to second server, and so on. So basically each service instance will have their own counter ranges, so it doesn't need to go to this counter every time to fetch the counter value. What's the problem here? The problem here is, let's say one service instance goes down, then let's say server 2 goes down, we'll lose this 1 lakh to 2 lakh counter range. Will that be a big problem? Because we can support counter values till 3.52 trillion, but we don't need that many unique short URLs. So if occasionally we lose few lakhs of counter ranges, that should not be a big problem. So we are good here. So we have achieved high availability in that scenario as well. Next comes the scalability part. So anyway, we are having microservice architecture, and if we are using any AWS like cloud services, of course these service instances will be auto scaled. So we have to configure few things, like after if those one service is, let's say 75% or 80% full, we need a new service. If one service instance is not being used, the usage is less than 20%, will reduce that service instance, and this type of auto scaling is supported in AWS or any other cloud services. So scaling part, we are good because we are having the microservice based this architecture. What else do you need for this system? Of course, we need health check and monitoring logging. So for any system, we need that because for any disaster scenarios, we need to log the data. We need frequent health checks and monitoring so that we can recover from any type of disasters very quickly. Now that we have some time, I'll just quickly cover the link analytics part. So here we are just keeping track of the number of times one link is getting clicked. So if you want to keep track of that, how we will do that? So this is coming in this path, right? Redirect to long URL path, right? So when user is clicking on the short URL, he is getting redirected to long URL. So in this path only, we have to keep track of the number of times it is getting clicked. But we don't want to do that synchronously, because our requirement is we need to have very low latency for the redirect fetch, right? So we don't want to hamper that. We want to have the analytics asynchronously. So for that, we can have a click event queue. So this service, whenever this redirect request is coming, is putting one event in this queue. That is basically will be with the short URL and few other informations whatever required, like who clicked, when clicked, and all the few things maybe. So and then there will be some worker nodes that will fetch from this event queue, and it will store it in some analytics database. So, and there will be one analytics service that will read from this analytics DB, and this analytics service can expose some API where using those the admin can keep track of the aggregated data. So now this is one way to implement the analytics path, but there are other ways, and there will be lots of other complexities for this analytics path. But our focus currently here is the URL shortener, so we'll focus on that, and this is our final design here.